The next speaker is Andrea Bulgarelli. He'll tell us about machine learning entanglement and lattice defects.
Okay, thank you. So what I'm going to talk about today is this recent work done in collaboration with this group of people, where we were able to provide a new numerical setup for the study of entanglement and defects by means of machine learning techniques combined to Monte Carlo simulations in the context of lattice field theories. So, a major reason why to study entanglement within the context of this collaboration dates back to this paper by Igor and collaborators, where they were able to show that entanglement indeed can be used as a probe of confinement. So, let me consider the ground state of a generic confining gauge theory. You may think of a lattice field theory. I'll be sticking to the lattice for most of this talk. But also, as it was done in that paper, a continuous holographic theory with a confining background. The quantity I'm interested in is the amount of bipartite entanglement between a portion of the space, let me call it A, and the complement B. And to do that, I need to pick an entanglement monotone, a natural choice, as Rocco told us about before. From the point of view of lattice simulations, is actually the Rényi entropy, related to the maybe more famous entanglement entropy. And the quantity I'm actually sticking to for the rest of the talk is the derivative of the Rényi entropy, the so-called entropic C function, which is a UV finite quantity, even in continuous theories, that encodes all the information I need to know to study confinement. So the behavior of this quantity is a function of the size of this slab in a holographic theory is as follows. As the length of this slab is very small, I'm probing short length scales of the theory, so what I expect, what indeed this quantity detects, are gluons being proportional to the number of colors squared. Then when I increase the size of the slab, the theory eventually hadronizes, and in holographic theories, there is this sharp first-order transition to a spectrum which is no longer made of colorful particles. For SUN gauge theories, it was conjectured in the very same paper that instead of a sharp transition, we might have an exponential decay, still signaling confinement. But to test this prediction, we actually need numerical simulations. So, how to do that? Well, as Rocco told us about before, the replica trick is a way to compute Rényi entropies by means of lattice simulations. So, let me go through it quickly by pointing out an aspect that will be important for our purpose, is the fact that the replica trick consists essentially in putting a defect in this replicated lattice. So, here is a 1 plus 1 dimensional system. Feel free to add whatever number of spatial directions you want. I'll be giving examples in 2 plus 1 dimensions, actually, the discussion is exactly the same. And I identify the subsystem A and the complement B here. And the replica trick consists in opening a cut in this system of 2 decoupled replicas and couple them together through this cut, defining a new lattice system. It can be demonstrated that the second Rényi entropy, for example, boils down to the calculation of this ratio of partition function between the system of coupled and decoupled replicas. That's for the Rényi entropy, but as I said, I'm interested in the entropic C function, that is the derivative. Here the discussion is very similar. I start from a system of already coupled replicas through a cut of a size L, focus on the edge of this cut, and I simply open another set. I eliminate this set of links at the edge and join the replicas together through this additional set of points to increase the length of the cut by 1 lattice spacing. And again, the ratio of partition functions encode the information on the entropic C function. That's what I need to compute. And now, the most important thing to keep in mind for the next 5 minutes or so to understand what's going on is the fact that the information on the entropic C function is encoded in a ratio of partition functions that are very close to each other. Actually, they differ for a very small subset of lattice links, in this case, essentially by a defect. So this approach can be used to perform precision calculations using Monte Carlo methods of the entropic C function. In this paper with Marco Panello this year, we performed actually the first thermodynamic and continuum extrapolation of an entropic C function in a gauge theory, the 2 plus 1 dimensional Z2 gauge theory. And the results can be directly compared to the theoretical prediction. And you see, we were able to fit the large length scale behavior of this quantity where the theory is expected to be confining with an exponential decay, not only an exponential decay, but really the exponential ansatz that was conjectured in this paper here. So we confirmed the theoretical prediction. This is nice, but one can say that this is just Z2. We are as far as possible from an ideal CFT scenario. It would be interesting as well to study SU engaged theory, possibly at larger and larger n to match this sharp transition. And to do that, the feeling is that either you have tons of core hours, or we might need something a bit more powerful than just a Monte Carlo. And the reason is that, as all numerical methods, Monte Carlo have advantages and disadvantages. A major advantage is the fact that the time you need to perform your simulations with Monte Carlo techniques is a polynomial function of the volume of the lattice. So we have this very nice scaling that is at the base of the success of the Monte Carlo techniques, the reason why we can study very large lattices. But the drawback is that Monte Carlo itself is computationally intensive. If you want, the coefficient in front of this polynomial scaling might be too large to obtain reliable results, especially for ratios of partition functions, that what we need to compute for entanglement measures, because Monte Carlo, it's not itself so well, it's not a quantity that you can measure so easily with Monte Carlo simulation. So the question is now if we can do better. And in the lattice community, there have been a lot of developments in the last, I would say, 3 years on the field of machine learning techniques, especially normalizing flows for lattice simulations. In a nutshell, a normalizing flow can be seen as a map between two probability distributions implemented as a neural network. These two probability distribution can be 2 points in the phase diagram of the theory, or 2 different lattice geometries. This is the case that we're interested in. And this transformation itself is very difficult to be worked out analytically, but we use the expressivity of a neural network and we train it to better and better approximate this transformation. The crucial feature of normalizing flows is that the Jacobian of this transformation, that is nothing but a diffeomorphism, is easily computable. And from the Jacobian of this transformation, we can work out the ratio of partition function between the two probability distributions quite easily. So now the question is if we can use these tools to perform large-scale simulations of entanglement quantity. And the answer is not really, because it's true that they are extremely powerful in computing ratios of partition functions for small volumes, but they don't scale as the Monte Carlo does. So that's a problem. We cannot push the simulation that far, but you see Monte Carlo and normalizing flows have somehow complementary skills. So the question we ask in our work is that if we can get rid of the problems of both the approaches, combining them in a common framework, taking the best of both worlds. And what we ended up with is an approach that we called the machine learning of defects. That is actually a quite simple idea, yet quite powerful, and is based on the introduction of a hierarchy in our simulations between the Monte Carlo and the normalizing flow. While the Monte Carlo takes care of the whole lattice, and it's very good at doing that, it scales quite nicely with the volume. While once we have a special set of points, whatever kind of defect you like, not necessarily related to entanglement, but it's a much more general approach, we go there with the normalizing flows, which is highly optimized, and the sampling is locally drastically boosted. So that's a quite simple idea, and we tested it in the 5 to the 4 model to study the entanglement entropy, the entropic function of the 2 plus 1 dimensional theory. That's hard for 2 reasons. First, in 2 plus 1 dimensions, there are not that many ways, efficient ways to compute entanglement measures. And second, the lack of scaling of normalizing flows makes it hard to push them to 2 plus 1 dimensional models. And we compared our approach to Monte Carlo methods, and this plot is quite nice because here we counted the time we need to simulate to reach a given precision in the calculation of the entropic C function as a function of the volume of the lattice. Here, the orange curve is the Monte Carlo, it takes some time to reach a given precision. The normalizing flow not only is better, but is progressively better and better for larger volume. That's something that doesn't typically happen with machine learning techniques. We were able to push our simulation to lattices that are very hard to reach with normalizing flows alone. And if you fix the statistics, the normalizing flow result is much more precise. So to summarize, we provided with this idea of machine learning with defects a new framework to study entanglement, but also other possible defects. Here I listed some of the potential applications. I will skip that for the sake of time, but let me just say that the idea is now to study really the entanglement in SU engaged theories. We are designing quite efficient flows to tackle SUN, SU3, but also SU engaged theories in 3 and 4 dimensions, and the goal is really to see this prediction and how they interplay between confinement and entanglement. Thank you for the attention.
Questions? Yeah, you go.
So you mentioned that you're seeing this exponential follow-up.
Yeah.
Were you able to follow it for a while? Or?
Up to here. I mean, here the length is measured in units of the mass gap. Here is one we reached about 3 times the.
So basically, you're sure it's not power law, right?
That's not power law. It's we're sure enough that it's exponential. We fitted that with the
That's what you would guess in the gap theory, right?
Yeah. And this is instead, it seems very close to a power law, the short landscape.
Oh, you can show the power law.
Yeah. That's a power law. It breaks down here, and then the exponential decay starts.
These techniques work equally well for the gap theory and gap theories and capless.
Yeah. The Monte Carlo itself works better with gap theory, but it can be done also with gap theories. Yeah.
Okay. Let's thank Andrea again.